data path, route selection, and forwarding. Essentially, the Edge Connect is also a router. It can forward packets between local interfaces if it knows which interface to use to reach the destination subnet. It could have this information as a result of being locally connected to the subnet, having the route learned via OSPF or BGP or from a static route, so that it then forwards pass-through traffic to the next top router. How do Edge Connect appliances learn about different prefixes and subnets for tunneling the traffic to other sites? Well, we use a protocol that is proprietary to Edge Connects called subnet sharing. Subnet sharing is used to exchange information between locally attached subnets to the Edge Connect appliances. The appliances also support BGP and OSPF routing protocols and can peer with third-party routers and layer 3 switches, enabling them to learn additional routes and advertise routes known to the Edge Connect appliances, usually with a preferred metric, so the appliances become the next best hop to reach the destination through the SD-WAN fabric. So here's an overview of subnet sharing. Again, it's a proprietary method that Edge Connect appliances use to share information about local subnets with each other, much like a routing protocol. The big deal is that it's done over a tunnel. So when a tunnel is up between them, each appliance can advertise its local subnets to its peers. When a packet enters an appliance on the LAN side, it can then perform a lookup in its subnet table and put the packet in a tunnel going to the correct destination based on the advertisements it's received. So EC1 shares its 10.10.10 subnet in a tunnel to EC2. EC2 shares its 10.10.20 subnet to EC1 via the tunnel. Now, the tunnel must be up. If there's no tunnel established between the two appliances, no subnet sharing can take place because, again, the advertisements go through the tunnel. If the tunnel goes down, those subnets are withdrawn from the route table. Subnet sharing is usually on by default. This is the switch, automatically advertise local LAN subnets. Other settings include use shared information. This basically says always use information I received from other Edge Connects via subnet sharing. Typically, you'll disable automatically advertise local WAN subnets because you're probably going to be using BGP on that end. The default metric that you'll want to know is 50 for subnet sharing. And you're going to access this through the routes page for an individual appliance. So this is a view of the routes table on the Edge Connect. All the routes on the Edge Connect appear here, including those learned via BGP, OSPF, or subnet sharing. Also, static routes show up, and you can tell because there's a way to delete it. And so this basically is useful if there's subnets in which the Edge Connect doesn't have an interface and can't learn via the routing protocol. Column I like to think of as the source column. This is where the route originated. There's also an administrative distance along with the metric. So standard route table, you can have your destination subnet, what your next hop is, or what interface it's forwarding out of. Unlike routes, which point to a next hop, routes learned via subnet sharing are associated with a destination appliance. So think of the destination appliance as the next hop. When you see auto or system, that means it's a locally attached subnet. So I mentioned administrative distance. The metric isn't the first thing that the Edge Connect will look at when it's determining which route in the routes table to use. There's a route selection criteria to ensure that the behavior in your network is predictable and deterministic. When an Edge Connect looks at its subnet table, the appliance will do a few things. First, it's going to consider the longest match. Let's assume we've got a packet destined for 10.10.10.4. It'll first look at its routes table and see, oh, I've got two subnets that I can use, two routes, one to 10.10.10.0/24. I'm going to prefer that because that's more specific than 10.10.0.0/16. If I have equal matches, then I'm going to break the tie by looking at the administrative distance. The administrative distance is basically how was the route learned. As you can see here, was it learned directly via IBGP? Was it learned via eBGP? Was it learned via OSPF? Was it learned originally from BGP but now redistributed via subnet sharing? So the lower administrative distance is going to be more preferred. If the two routes are the same prefix and they were learned via the same source, then we'll look at the metric. Right? The lower metric is preferred. If the metrics are the same, what you'll want to do is you'll want to configure a peer priority. You want to make sure that your network routing is deterministic and predictable so that you can control the traffic and have traffic be treated exactly the way you want it to. So it's recommended that you configure this peer priority. Because if you don't configure a peer priority and everything else is equal, what will happen is the route will be chosen at random. And then if it's chosen at random and if you don't have your rules configured properly, traffic may not behave exactly the way you think it will. And the last thing I want to talk about is management routes. Each appliance maintains a management route table for self-originated traffic, like connections to the cloud portal, or NTP, or SNMP. Any static routes you add to the management routes table, except for default routes consisting of all zeros, are also copied to the data path route table. Additionally, if you ping from an appliance, it will come from the management IP address, unless you specify a source. We'll see that later when we talk about ping, but just know that there's a management route table that plays into effect. When you go into the ASD course, we actually don't use the management interface for managing. We actually configure loopback addresses and use loopback orchestration.